Okay.
Cool. My next stop with this machine is going to be Bob, so I'm going to have him set up and ready to roll. We should have no problems, and it should only be about a minute break for the orange can thing. So.
All right. Well, go ahead. I'll give you a call if we run aground on time, but Dolores, I'm going to give you a little more time since it's 7:15. We'll expand your time by a few minutes to make sure you get your presentation in. And yes, you have an adoring public waiting on you. And I don't know where the stream numbers went. They should still be there. I saw like 43 folks. Oh, concurrent viewers. 41, 39. Okay, they're there.
Excellent.
All right. So let's get going.
Have a great time, Dolores. Thank you very much.
Yeah.
You're welcome.
Okay. Yep.
My pleasure.
Doug Bach says, hi, Dolores. I am going to read a little bit of a bio and let you get going. This will be
all right.
Quick because I'm going to find a schedule. Of course, we could all read your bio online, but I'm going to officially kick it off. Welcome to another headline presentation at Astronomy at the Beach. We have the esteemed Dolores Hill. This will be real quick, Dolores. We have a former resident of Michigan. Why would you ever want to leave our cloudy skies? I mean, we don't understand that. But anyhow, you are a meteorite specialist at the University of Arizona Lunar and Planetary Lab. You are also a public outreach specialist with NASA's OSIRIS-REx mission to asteroid Bennu, operated by, is that JPL?
No,
it's LPL.
University of Arizona.
Okay,
and Goddard Space Flight
University
Center.
of Arizona. All right. Oh, that LPL, the Lunar and Planetary Lab. So the goal of OSIRIS-REx is to collect a sample of Bennu in mid-2020, which we'll find out if that worked or not, and return it to Earth in late 2023. Bennu turned out to be rockier than anticipated, but mission planners have now identified 4 sites on its surface that are smooth enough for OSIRIS-REx to collect the sample. It also says that you will fill us in on the latest news about the sites chosen to be sampled and what we've learned so far about this fascinating little neighbor of ours in space. So I am going to get out of the way without further ado. Take it away, Dolores.
Thank you so much. Well, it's a great pleasure to be here today, and I'll go ahead and share my screen and get started. Okay, I think we will here. That's the one we want. Let's see here. Can everyone see that? Hopefully you can. All right. Well, greetings.
Try it again. I just gave you co-host, so try sharing again. I think you've got it now.
Okay, we'll try it again. And share.
There you go.
All right. So
right,
we'll start from the beginning. Wonderful. All right. That's perfect. Okay, thank you so much. Well, greetings from the OSIRIS-REx mission and to all our friends in Michigan. I'm sorry Rick can't be with us today, but he says hello to all of you. This NASA mission is a partnership between the University of Arizona, NASA's Goddard Space Flight Center, Lockheed Martin, and many others. Very soon, the spacecraft will collect a sample of near-Earth asteroid Bennu and return it to Earth in the year 2023. We expect this to be our country's largest sample return since the Apollo missions that brought back rocks from the moon more than 50 years ago. So today, I'll report on the mission status and our readiness for TAG. The mission was approved back in 2011, and it was launched from Cape Canaveral in 2016. We arrived at Bennu in 2018, and we just completed our critical Matchpoint rehearsal that brought the spacecraft closer than ever asteroid Bennu, only 40 meters, 131 feet from the surface. This is the first opportunity to collect a sample, will be in October 20th, 2020. And there's plenty of margin built into the schedule to ensure mission success for this never before tried procedure. We are not landing on our asteroid, we are only touching it for a few seconds. So I wanted to show some pictures of the spacecraft during assembly at Lockheed Martin in Colorado and the exciting launch from Cape Canaveral, Florida. It was proclaimed a near perfect launch. So why would we want to go to an asteroid? Well, because they are the first solid rocks to form in the solar system. And like snapshots in time, they reveal the formation and history of the solar system. Some asteroids have not changed very much since they were formed, and others have been radically transformed by collisions and melting. We chose one that has not been transformed very much. Meteorites are pieces of asteroids that collide with Earth and provide clues to their parent asteroids. Unfortunately, for most of them, we do not know which asteroid they came from, so our understanding is hampered. OSIRIS-REx provides important truth information for asteroid Bennu by comparing astronomical, remote sensing, and sample analysis information. So what about that name? Wow. The mission's name is actually an acronym that includes the objectives of the mission. Origins, for understanding the origin of the solar system and organic materials important to life. Spectral interpretation, for the spectrometers that provide composition and thermal properties. Resource identification includes looking for commercially important materials and water that is needed for humans and mining activities. Water is an important commodity in the solar system. Security refers to investigating how asteroids in the main belt migrate toward the inner solar system to become near-Earth asteroids. And finally, Regolith Explorer is the last and most important objective of the mission: to return a 60-gram sample, a pristine sample of the regolith of Bennu. And regolith is just our scientific term for dirt on an airless body like the moon or an asteroid, but very important dirt. Even though we have meteorites in Earth's laboratories, we are collecting a pristine sample of the early solar system that has not been heated by passage through the atmosphere, corroded by Earth's water and oxygen, or contaminated by fingerprints and life on Earth. Our target asteroid was originally known as 101955 1999 RQ-36, after its discovery sequence. Early on, we obtained permission to hold a naming contest for school children. 9-year-old Mike Puzio suggested Bennu, a beautiful that was associated with the Egyptian god Osiris. That set the theme for official names of features on Bennu as well. They are named after mythical birds. So where is Bennu located? Most asteroids are located in the main asteroid belt between Mars and Jupiter. Some belong to collisional families. Bennu orbits the sun in an orbit that is entirely inside the orbit of Mars, as you see here. Indeed, the orbit crosses that of Earth in 2 places. Thankfully, not in 4.5 billion years, and probably won't for a few hundred to come. Bennu's size and orbit qualifies it to be labeled a potentially hazardous asteroid. This is an astronomical term, not necessarily a qualitative term, but it's something we will be keeping track of. And it may be a member of the new Polana family or the Eulalia family of asteroids. How in the world did we choose just one? When we were planning our mission, there were only 500,000 asteroids known. Today, there are more than 990,000 known. They were there the whole time. It's just our ability to discover them has greatly improved. But we selected one based on the fact that we needed one that was nearby, that we could reach with a reasonable amount of time and fuel, and one whose orbit was easy to get to and return from. Out of 192 possible targets, we needed one that was larger than 200 meters across. That's because astronomers have learned that asteroids smaller than this threshold rotate so fast that they can't hold on to their loose surface material or regolith. We need loose regolith. Bennu is 500 meters across, so it is perfect. Next, we needed to know some spectral information from Earth-based telescopes to select a stony, carbon-bearing asteroid that might contain organic materials. In the end, there were two ideal candidates. Originally, we selected Ryugu. Then our asteroid astronomer discovered radar data that provided the shape and dimensions for Bennu. It gave information that there was probably loose material on the surface, and our spacecraft team, the flight dynamics teams, could prepare many calculations ahead of time and refine them as more precise data were acquired. So we switched targets and selected Bennu instead. I'm not going to go into a great amount of detail on our instruments, but I would like to point out that we selected the perfect suite of instruments to study an asteroid. 5 instruments are on board. Starting in the lower left-hand corner, we have OVIRS for the OSIRIS-REx visual and infrared spectrometer. OTIS is the thermal emission spectrometer. OCAMS is actually a suite of 3 different cameras. One is essentially a telescope, the Polycam, MapCam, and SAMCam. Then we have the REXIS instrument, which is the regolith X-ray imaging spectrometer built by MIT and Harvard students. And over on the right, we have OLA, the OSIRIS-REx laser altimeter, contributed by the Canadian Space Agency. It's the device that allowed us to truly understand the topography of our asteroid. So let's take a step back and look at what we knew early in the mission and what was revealed as we approached Bennu. Bennu from Earth will always appear as a faint dot in the world's largest telescopes, as you see in the lower left. Even so, the Arecibo radio telescope in Puerto Rico was able to bounce radar beams off the surface and determine Bennu's shape and dimensions. The predicted shape was perfect, as you can see in the spacecraft comparison on the right. By exploring a known asteroid and bringing back samples to analyze in detail, we will calibrate astronomical measurements and refine theories to greatly advance our scientific understanding. Since I'm a meteorite person, I wanted to show some examples that are similar carbonaceous meteorites that are the closest analogs to asteroid Bennu. Notice how dark these are. They are black, and Bennu is as well. It only reflects 4% of the sunlight that strikes its surface, making it as dark as a piece of charcoal. So our sample collector will contact the asteroid surface for 5 to 16 seconds, as shown here, much slower than shown here actually. The spacecraft will slowly approach the surface, and once we make contact, a blast of high purity nitrogen gas will flow through the collector. Once we've verified we've collected our sample, we'll stow it in the sample return capsule. Close it up, and at just the right moment in 2021, start to head back towards Earth. So how do we actually collect our sample? Well, we use a device called the TAGSAM, the touch and go sample acquisition mechanism. It gently touches the surface. We used this test in the Vomit Comet to show that it would actually work in a low gravity environment. The test showed that we're capable of collecting up to 2,000 grams versus our 60-gram baseline. Contact pads on the bottom will collect fine particles too and provide our contingency sample if for any reason the gas tanks don't fire. The diagram on the left shows how nitrogen gas will flow through the 15-inch diameter tag SAM head. Gas flows out through the side mesh while rocks and particles are trapped inside. And there they go. What if the tag SAM touches a spot that contains larger rocks, as in this example? Here's a test that included 10 centimeter or 4-inch rock obstructions that prevented the tag SAM from fully contacting the surface. Thankfully, this test, along with many, many others, was successful and provided a large amount of material. Once we've verified that we've collected our sample, in 2021, the spacecraft will depart from asteroid Bennu. In 2023, as it travels past Earth, the sample return capsule will be ejected and arrive at the Utah Test and Training Range west of Salt Lake City. The heat shield will protect the precious sample inside, and a parachute will deploy for a softer landing. Our team will be waiting to take it to a special clean room that is being built as we speak at NASA Johnson Space Center in Houston, Texas. Once the capsule is returned to Earth, the world's meteorite laboratories will begin analyzing the long-awaited samples. As you can see, many of the instruments shown here are too large and too sensitive to fly in a spacecraft. So that's why we need a returned sample. Here is the first close-up view of asteroid Bennu. Its shape was just as expected, down to Ben, the big boulder on the lower right-hand edge. However, pre-launch thermal inertia models indicated we should expect smaller rocks over the surface. We learned that the models need adjustment. The large boulders and rocks challenged the team to locate a suitable sample site, but I assure you we did it. So here are some highlights of discoveries we've made so far. As I've said, we discovered boulders, huge boulders, up to 60 meters or almost 200 feet across. Wow. Rock slides, ridges, thermal fractures, and impact craters as well. Early on, we discovered water in the rocks. These are locked in the minerals and indicate that there has been flowing water somewhere in Bennu's parent asteroid. We also discovered minerals transformed by water, phyllosilicates or clays, and magnetite, which is an iron oxide that often forms in the presence of water as well. Bennu is a close match to some meteorites in the laboratory, such as the ones I showed you earlier, and yet it has some intriguing differences that we'll be watching for. The sun's radiation on Bennu's black surface causes its day to speed up by 1 second per year. And yes, we did measure that because we had a long baseline of measurements. The position gets closer by 131 feet per day. That is, its orbital position gets closer to the sun. The discovery of a black hole in outburst by the student instrument RExus was pretty exciting, and I'll show you a picture of that in a moment. And one of the most exciting discoveries of the entire mission were particle ejections from the surface of our asteroid. So let's look at the black hole that the student instrument RExus discovered. You can see the limb of Bennu in the lower right. Here it is clearly above the noise. All right, so what about those particles? Wow. The particle ejections from the surface were discovered by mission astronomer Carl Hergenrother by accident. Being a good astronomer, he wanted to identify the background stars in the spacecraft navigation images. He noticed a star cluster that he couldn't identify and eventually realized these particles were moving while the camera took the image and converged to a point on Bennu, meaning they were moving very fast and coming from Bennu. This is the first time they have been seen anywhere in the solar system. They could be the result of micrometeoroid collisions with Bennu and or particles from rocks as they fracture in the thermal stresses of daily hot-cold cycles from minus 100 degrees Fahrenheit to 200 degrees Fahrenheit every 4.5 hours. It could be a combination of the two. So the science team wanted to make sure that these particles would not pose a hazard to the spacecraft and understand them better. It turns out the particles are between 1 and 10 centimeters in size. They are ejected at speeds of 0.05 meters per second to 3 meters per second, actually Bennu's escape velocity. So some of them fall back to Bennu immediately, some orbit for a short while, and some are ejected out into space altogether. The team followed the trajectories of each particle, measured their brightnesses to learn more about Bennu's gravitational field. Thankfully, there is no danger to the spacecraft. Unfortunately, the locations and timing of these events is not predictable, and there's no obvious physical evidence left behind on the surface. So that's definitely one thing we would like to investigate further. All right, so let's take a tour of asteroid Bennu, close up. As I mentioned earlier, it exhibits impact craters that were formed when it collided with other asteroids, very much like craters on the moon are made. The largest 130-meter, 126-foot crater is a significant fraction of Bennu's size and perhaps could have disrupted it into many fragments, but didn't. So that gives us information about the underlying strength of the asteroid. And there are regions that contain very large boulders. Even the smallest ones in this image are far too large for our 15-inch collector. Notice there are rocks on top of rocks, angular rocks, jumbled rocks, where they have moved and migrated between huge boulders many meters across. The small angular rock in the middle is the size of a dump truck. So these are huge. Also, we are interested in rocks that are breccias or broken up rocks made of different materials. And are those white rocks pieces of different asteroids? Hints of things to come. So these all posed challenges for us. Here's another example of a huge boulder field. The red circle is the original 30-meter radius that we needed to be flat, smooth, containing small rock fragments, 2 centimeters across or less, suitable for our tag SAM collector. So this would be a terrible sample site. Thankfully, Lockheed Martin, the navigation team, and the flight dynamics teams determined that they could accurately maneuver the spacecraft to a target circle of only 5 meters in radius after all. So the green circle is our new criterion. Thankfully, the science team was able to identify many regions that would fit this new criterion. They down selected to a list of Sweet 16, then down to an Elite 8, and finally to a final 4 good sample sites. All right. So getting back to those boulder types, there are basically 2 types of boulders on asteroid Bennu. Hummocky, or sometimes referred to as cauliflower rocks, and bright and smooth rocks. We, at this point, don't understand the differences or their origins. We know there are some thermal inertia differences between these rocks, possibly some very, very slight compositional differences. But we'll be looking for more information about this, these kinds of rocks in the sample that is returned. Jamie Malaro and her team looked at the fractures in all of these rocks. We'll go to the next image for that, and was able to look at the kinetics involved long these fractures took to form and grow. These fractured rocks formed from many thermal cycles as rocks on Bennu were exposed to high temperatures when facing the sun and very cold temperatures when in the shadows and darkness of space, every 4.3 hours for 4.5 billion years. These fractured rocks look a lot like those that we see in the desert Southwest for comparison. So for an example, Tucson ranges from 70 degrees to 100 degrees Fahrenheit in June, and we see rocks like these. I mentioned those white rocks. Well, we've determined that at least 6 boulders on asteroid Bennu are probably from the asteroid for Vesta. We think these may have been incorporated into Bennu's parent asteroid when it collided with material from Vesta. That material broke apart and reassembled into smaller rubble-pile asteroids like Bennu. There may be other asteroidal materials mixed in with the sample that we bring back as well. So we'll be looking for sort of a 2-for-1 or a 3-for-1 collected sample. So how did we determine that this bright material was from Vesta? We looked at the spectral trends for these boulders and determined that they matched material from Vesta, and Vesta has a very unique signature in meteorite spectra. We have meteorites from Vesta, and we were able to compare the spectra with those. Some of the boulders are clustered by each other, and they are not equally distributed throughout the asteroid. But you can see in the lower right the average Bennu brightness and reflectance and the spectral information, and that the other boulders form a trend. All right. So from all of these sample sites, how did we select our best one? The primary and backup sites are informally referred to as Nightingale and Osprey, after birds again. And they were selected using 4 criteria, with safety of the spacecraft being number 1. If the spacecraft isn't safe, nothing else matters. Sampleability refers to the right mixture of rocks and particles that we desire. Deliverability refers to the ability to deliver the spacecraft safely to the site and to be able to deliver material into the tag SAM. Last is science value. That's okay. The science team constructed a variety of global maps containing composition, heat maps, rock sizes, fractures, hazard maps, etc., and carefully evaluated and scored every site. We will actually be able to learn valuable information from any sample returned from Bennu. So all sample sites are scientifically important. Many of the boulder measurements that were done, you see in the upper right-hand panel, were made by CosmoQuest Bennu Mappers Citizen Science Program. And if any of you helped us with those measurements, we thank you. We definitely needed the help, and it was a great help to us because there were many more boulders than we were expecting. So that part of the mission took more time than we had planned. Thank you. So with that, let's go and look at our primary site. So the primary site, Nightingale, is in Bennu's northern hemisphere. And there are some smooth areas within this crater region and some big hazards nearby as well. Most of the sample sites that were selected turned out to be within craters. Those seem to have the flattest, smoothest areas. And you start to get a hint of the site's challenging topography, looking at that huge upper right called Mount Doom. It's the one up in the upper right and looks tricky. At this site, we expect plenty of unresolved, or what we refer to as fine-grained material below the resolution of our camera at this point. So this is a good site, and the spacecraft team can get us in pretty smoothly. The backup site is called Osprey. This was a very fascinating site as well. It's near the crater, near the equator of, and again, there are smooth regions. There's that light-colored boulder that you see within the smooth crater. The science team is especially interested in that edge in the center. We don't know at this point if this is fine-grained organic material or if it's dark colored boulder peeking through the bottom of the crater. And so that was a very interesting site for that reason. We're looking for organic materials, not life, but made from oxygen, carbon, and hydrogen. This schematic illustrates some of our recent rehearsals. It shows our departure from Bennu orbit, which is near point 1. Point 2 is our checkpoint rehearsal, where we depart from that orbit very, very steeply and start to descend down to the surface of Bennu. And then match point, where we actually start to match the rotation period of Bennu. Then we tag and return to static orbit around Bennu, ascertain how much material we have collected, and once we've confirmed an adequate sample, we stow the sample in the sample return capsule. So I'm going to show you some real images from those maneuvers that helped the science team prepare for tag. All right, this was our successful checkpoint rehearsal, and those few images took over 10 minutes to acquire. So we are moving very, very slowly. This first rehearsal allowed us to test the natural feature tracking at the Nightingale site. We uploaded a special atlas of rock hazards, and the spacecraft compared what it saw with that atlas. Because we are going to be 15 minutes away from asteroid Bennu, much of the sample collection will need to be semi-autonomous. And so this natural feature tracking procedure allows the spacecraft to wave off or continue as it proceeds. So we'll go take a step back to the match point rehearsal and look at the navigation camera. This is from NavCam 2 as we left orbit and started to approach the Nightingale site. This was on August 11th. So these are images taken over a 3-hour time period. It's actually kind of excruciatingly slow, but safe is good. These are pictures as we return to safe orbit. Next, 7 minutes before the checkpoint burn, the OCAM's MapCam camera began taking images. And you can see quite a lot of rocks below us there. The blue boxes on the right illustrate the region corresponding to the images. So immediately before performing the checkpoint maneuver, the SAM or sample camera also began to collect images. And now you see the sample arm in the field of view. We're going to document our sample collection to understand what occurred when we collect our sample. So over a 13-minute time period, we take these pictures, and the smallest rocks in the final fields of view are only a few centimeters across. So this would be a good site. And the spacecraft will be able to maneuver a little bit within that area for safety. All right, so now let's go ahead and fly with the spacecraft over the Nightingale primary site. This movie combined images from OCAMs, the laser altimetry data from OLA, and the resulting digital terrain model that was overlaid on all of those data products. So here you get a real feel for how rugged the surface of Bennu is. The flight dynamics team has devised the perfect trajectory to get in and out of the site to collect the perfect material safely. We need to get into the site and out of it without touching any rocks whatsoever that might cause the spacecraft to crash. So looking in 2 dimensions, it doesn't look too horrible, but in 3 dimensions, we need that extra information. So the OLA instrument was very important for us. Now let's take a trip over the Osprey site. Again, you see that dark material in the middle. You see that huge boulder that is maybe 3 meters long that we want to avoid. But there's plenty of clear space to get in and out safely. And you see the horizon of Bennu as well. And there we go. So what is next for OSIRIS-REx? Well, October 20th is our tag maneuver, or our touch and go maneuver. Note that the orientation of the spacecraft and the timing of the maneuver were determined by sun illumination. We need sunlight on the surface in order to document the collection. The sample and instruments have temperature constraints as well. And we wanted adequate deep space network communications. The entire tag maneuver will take about 4.5 hours, slow and careful. The spacecraft will leave the safe home terminator orbit, and 4 hours later, at a distance of 125 meters at checkpoint, we'll begin our steep descent, as you see here. The Matchpoint burn will take place at 54 meters and take the tag SAM the rest of the way down to contact. After the tag maneuver, the spacecraft will return to safe orbit, and the SAM cam will be the first camera to confirm sample collection inside the tag SAM head. Then we'll do a spin maneuver with the arm extended to determine the sample mass before and after collecting our sample. That will occur on October 24th. So I'm happy to tell you that the best of Bennu is yet to come. Thank you so much for joining us today, and we hope that you'll join us on October 20th to watch along with the rest of the team. Thanks again. And thank you for all our friends.
Sure, there's some applause going on out there in the internet world. We do have a few questions and comments. We'll start, let's see, I'll start from the top. Bob Trimbley, who had met you apparently a while ago.
Oh, yeah,
Saw and you may remember him. He
I
asked,
sure do.
good, is the spacecraft mothership going to be repurposed?
We hope so, but that is up to NASA.
Okay.
The spacecraft will fly past Earth, and at that point, if the instruments are still in good working order, they could still be used for remote sensing. We would not be able to collect another sample, however, because the sample return capsule is coming to Earth. But that's
Okay.
all to be determined.
Excellent. So Dave New has a couple of comments. He had asked, how do you match the rotation of the asteroid? Not enough gravity to orbit it, he would presume. And he also mentioned, seems you'd have to align with either the North or South Pole and do a roll maneuver to match, then only 2 sample sites to choose from, which I think that's what you ended up with, were 2 sample sites anyhow. So let me know if you need me to reread the question, but that's from
Okay.
Dave.
No, excellent question. So you're right. Bennu is so small and has such a small gravitational field that it's actually difficult to stay in orbit around it. It's not like the moon or Mars where you can approach at that sweet spot and get trapped into an orbit. We had to actually use a variety of thrusters to keep us in orbit. And so we're going to match the rotation rate of Bennu using very small thrusters.
Okay. So we have Jay Ilines one, who says this is absolutely amazing that those maneuvers can be done when you were showing the maneuvers, and
Yes.
also mentions wonderful presentation.
Oh, thank you.
Yep. Harmony
Yeah.
Smurf, who is in one of our astronomy clubs, Seven Pond. I keep introducing you, Harmony. Harmony is a member of these clubs, who says, exciting detail already. Thanks for the show.
Oh,
We have Dale Wilson. Is the rotational axis of Bennu stable, or does it precess?
oh, I believe it does precess a very small amount, but it's not wild. You know, it's not like a tumbling asteroid for those who like to measure light curves.
Okay, so let's see. I'll say Dajode Ward. That's your screen name here. It says very interesting, and I'm sure there were more that would say the same thing. Samir and Muli says, hi, Dolores. I'm starting a space club at my high school, and we want some guest speakers to come and talk about what they do. I'm going to skip to his other question, where he says he was wondering if you would be able to come and speak sometime at our club about your work on OSIRIS-REx. He would totally understand if you're too busy and cannot come or do not want to. This would be over Zoom, which Samir, we're using Zoom as the primary stream, but we are streaming it to YouTube. So Dolores, how would Samir get in contact with you?
I recommend just sending me an email to dhill@lpl.arizona.edu is probably the best way.
So I'll type it in the chat, dhill@lpl.
Arizona. Oh, yes. .arizona, all spelled out. .edu.
Okay. So I've typed that out. So a couple more questions here I think I can get through, including yours, Dale Parton. I'll get down to yours. Dale Wilson says, great presentation, Dolores. Dave New says, thank you, I think, for reading his question. and for the presentation, I'm sure. Bob
It's
Tremblay
my pleasure.
is telling everyone, head on over to the Ask an Astronomer panel when you're done here, which we have a couple of astronomers that are there to ask questions. I've got to head over there too to moderate it, but we'll take some more time to finish through these last questions and comments. Chris Nichols says, great presentation. Great to know what investments are being done for science. And he's also from the Seven Ponds Astronomy Club. So we have our,
Great.
I want to say 9 or 13 astronomy clubs that are all a part of our organization, and they are growing.
Well, I used to belong to the Warren Astronomical Society and the Sunset Astronomical Society.
Okay. I just joined the Warren Astronomical Society recently, and I'm a member of the University Lowbrow Astronomers, Ann Arbor, Michigan. Go Blue. Dale Parton has a good question. So if we get much less, if we get much less than 60 grams, do we try again?
That is for NASA headquarters and the sample board to determine. So the team will assess the risks and hazards involved with doing that. They could go back if they had to, but whether they would want to take that risk is not clear at this point. It would depend on the circumstances. So it's to be determined. We could. We have 3 tanks of nitrogen gas to collect samples, so we could have 3 tries if we wanted to.
Okay, excellent. So 3 strikes and you go with what you were able to collect is what it sounds like. So,
and those contact pads on the bottom will collect a significant amount of material as well.
Okay.
So if for any reason the gas didn't fire, that's okay. We'd still collect something. Maybe not the ideal mass, but we could.
You'll have something, which just have to be more careful, and hopefully on re-entry nothing gets damaged. I'll throw in a quick question. Anything tested as far as the re-entry capsule? Is it just all proven materials from other flights that you're using?
Yes, excellent question. So the sample return capsule is based on the Stardust mission's capsule with a few improvements. And it was selected because it will protect our sample. The sample will not get heated. And we have witness plates on the inside to test for any contamination of the sample as well.
All right.
So it'll
that sounds like great. It's tested. It should return safely.
Yes.
So we'll have to be looking out to see what news comes out. Some of it'll come out on media. I'm gonna write quickly, and then we'll call it a presentation. Thank you so much. Great presentation from Mirren again. I echo those comments. All questions were answered. Great Lakes Association. So it's one of us that it's on the board that chimed in. I'm guessing John Walbank, but I'm sure I'm wrong. But Dale Thiem, who is also in the Warren Club, you've been made a lifetime member.
Oh, so that's wonderful.
You are a part of WAS, and along with Rick. So the both of you are lifetime members of the Warren Astronomical Society. Feel free to join in on our meetings on any time. We'll have to send you the email with the meeting information for next month if you are interested in joining and listening in. So thank you for those who asked all the questions, gave comments. I think we were close to 50 folks listening in, and there will be more as people watch the recorded version of this over the next few days. So thank you again, Dolores.
My pleasure.
An excellent presentation. I was curious as to where we are
Mhm.
with the with Bennu and if we had collected anything yet, and so we know it's coming.
Almost.
Looking forward
Yep.
to that. So thank you again. I'm going to go ahead and
My
stop the
pleasure.
stream. And thank you for all that attended the stream and continue to enjoy virtual astronomy at the beach. Do not forget to fill out our survey at the top of the page, the GLAC.org page. Thank you.
Thank you.
All right. And you can go ahead and